So hello everyone, today we'll be discussing about rearrangement reactions. So this video will be basically on rearrangement reactions, the factors which drive the rearrangement reactions, and also we will discuss two named rearrangement reactions. Those are Wagner rearrangement reactions and Pinacole Pinacolone rearrangement reactions. So before discussing about rearrangement reactions, what should be the first question that comes in our mind? That is, what is rearrangement? So let's take an example. If we take a chalk, a pencil and a pen, and we again arrange it in this way, then we can call this as an example of rearrangement. Okay, so after we had a simple idea what is rearrangement, let's come to rearrangement reactions. So rearrangement reactions are a set of reactions in organic chemistry in which the basic skeleton of the molecule gets rearranged. Okay, so let's take a simple example, this one. Which gets rearranged to give us this product. Okay, so after we had an example of rearrangement reactions, we got a basic idea what is rearrangement. Let's talk about the factors which drives the rearrangement. So let's take a simple example. Before going to the example, let me clear you one thing, that in this video I'll be talking basically about those reactions in which carbocations are involved. So let's take an example. This molecule, and we add some silver ion and ethanol. So what we are getting as a product is this one and this product. Okay, so if we now let's look at the mechanism. So this was our parent molecule. We added some silver ion source which will eliminate AgBr to generate a carbocation. So since this carbocation is 1 degree carbocation, it gets rearranged, means this methyl group will get shift to this position to give us methyl in this position and the positive charge here. So what we see the difference is, this is a 3 degree carbocation. Okay. Now we know that for carbocation, stability order is 3 degree carbocation is the most stable, then comes the 2 degree carbocation, and then the 1 degree carbocation. So we can say that what is the driving force in this reaction? The 1 degree carbocation is getting rearranged to form a more stable 3 degree carbocation, and this is one of the factors which drives a rearrangement reaction. So is it so that there is only one factor? which drives a rearrangement reaction. Let's look at another example. We have this molecule. We have this molecule. Okay, yeah, this one. So its name is alpha pinene, and when we add H plus source, it gives us a product which is this one. Its name is little complicated. It is isobornyl chloride. Okay, so let's look at the mechanism. So what happens when it gets the H plus source? A carbocation is generated in this position. Now what happens? This bond breaks and this carbon along with its bonding electron attacks here, and what we get is this molecule. So it may arise in your mind that this carbocation was a 3-degree carbocation and this is a 2-degree carbocation. So why is this molecule is getting rearranged from a 3-degree carbocation to a 2-degree carbocation? The reason is ring strain. We can look in this previous example that it is a 1, 2, 3, 4 membered ring which is highly strained. But in this example, after it gets rearranged, we find a 5-membered ring which is comparatively less strained. So although it is converting from 3-degree carbocation to a 2-degree carbocation, but the ring strain plays the major role here. Means the decrease in the ring strain is the major factor which drives the reaction towards this. So after we discuss about rearrangement reactions, now let me ask you a question, that are rearrangement reactions are blessing or curse? So what would be your answer? The answer is simple, it depends. Well, so I told the answer it depends. So why it depends? Because in some reaction, like we just saw here, that we give exclusively this product as the major product. Okay, and also there are some reactions in which due to this rearrangement we get a mixture of products. Let's take a simple example, which is Friedel-Crafts reaction. In Friedel-Crafts reaction, what happens? Suppose we did the Friedel-Crafts reaction and we got the product, this one, which is paraxylene. Okay, so we cannot simply isolate this product. Means in addition to this product we also get some other products like this one. So what happens here is that due to the presence of the acid source, we generate electrophile. Here, and this bond attacks here, and after rearrangement we get the meta product also. So what can we say? We can say that in the first example it's like a blessing because we are getting only a single product, but in the second example it's like a curse because we are getting paraxylene and also metaxylene. So you got the answer that rearrangement reactions can be blessing and also can be a curse. So next comes types of rearrangement reactions. There are two types. One is simply intramolecular and another is intermolecular. So what happens in intramolecular? Here the migrating group does not get completely detached from the parent molecule. Means we can say that in this intramolecular rearrangement reaction, the migrating group migrates from one position to the other without completely detaching from the parent molecule. But in case of intermolecular rearrangement reactions, the migrating group, suppose the R group, first get detached and it again gets reattached to the second position. So it is intermolecular rearrangement reaction. So let's come to our name reaction, which is Wagner name rearrangement reaction, which is Wagner Meerwein rearrangement. Okay, so let's take a simple example. OH H H R R R. So if we protonate it, then we will get this OH2 positive. Here are two hydrogens, R R R. This could be same or different. So after the elimination of H2O, a primary carbocation is generated in this position and one of the methyl group migrate to this position to give us from a 1 degree carbocation to a 3 degree carbocation. Okay, and from here minus OH plus takes place to give us this product. So this is a very simple example of Wagner Meerwein rearrangement reaction. So let's take another example. And if you alternate it, I hope you can I hope you can tell what will be the product and what will be the probable mechanism. So as this is a very simple reaction. This H plus this lone pair present here will absorb this lone pair in the oxygen will take up this proton, to generate a very good leaving group to positive, and after the elimination of water molecule we generate a carbocation in this position. The methyl group migrates here and a carbocation is generated in this position. After that minus OH plus takes place, we get a product this. Okay, so I hope you all are getting bored after studying all this reaction. So let's go in a race. In a race between alkyl and aryl group. Suppose an aryl group pH and CH3 both are running to migrate. So what do you think? Who will win this race? Well, it has been found that if the R group is CH3 and its rate is 1, then if the R group is a phenyl group, then its rate will be more than 1000 times faster. Means phenyl migration is about 1000 times faster than methyl migration. What is the reason behind this? Well, if we can look at our example, if it is a phenyl group, then we will develop, during migration we will develop a phenonium ion in which the positive charge is delocalized in the entire ring. This gives an extra stability to the phenonium ion. Okay, so as it involves a positive charge delocalization in the ring, so any group, if we attach some electron withdrawing group, then it will decrease the rate of migration, and if we replace it with some electron donating group, then it will increase the rate of migration. So the order could be, if we have para position, in the para position if we have OMe, it will be fastest. Then if we have a simple phenyl, then suppose PCl, a electron withdrawing group, then come methyl and hydrogen. Okay. Now let's come to another example, another set of reaction which is known as Pinacole rearrangement. In Pinacole rearrangement reactions, a diol, when it is protonated, it gets converted to a ketone. So the probable mechanism is, it is also a very simple reaction in which OH2 positive is generated, and then this group leaves to generate this ion. Now what happens? One of this group migrate to this position to generate a positive charge, or the cationic position, to shift the cationic position to this position, to this carbon. So to stabilize this carbocation here, the lone pair will attack and it will form a double bond. So till this step it is similar to Wagner Meerwein reaction, but it changed because from this step, because the lone pair in the O oxygen attacks to the cation, to the carbocation, to produce a double bond here. So the stability of this CO bond is more than carbocationic stability. Means if there is a chance that after rearrangement, suppose a 1 degree carbocation is converting to a 3 degree carbocation, and also if there is a possibility that after migration a C double bond O bond is formed, so the reaction will proceed in the second way. The migratory aptitude is also similar to Wagner reaction. That is, para position OCH3 will be faster than normal phenyl, then chloro and parachlorophenyl group. Then we will have the methyl and at last the proton or the hydride shift. Migratory aptitude versus carbocationic stability. So let's take an example, this one. Whose name is 1,1-dimethyl 2,2-diphenyl glycol. So what product we will get is that we will get PH Me methyl 12.0. So this is a 3,3-diphenyl 2-butanone. So from our previous concept, we might have thought that the phenyl group should migrate, but what is happening here is that the methyl group is migrating. So can you think the reason? The reason is, here the proton from the acid source has a choice to attack any of the OH group, but it will attack that OH group which will generate a more stable carbocation. Okay, so what the proton will do, it will attack in this position to generate OH2 positive, and when the water is eliminated, it will generate a carbocation in this position. Now this carbocation is stabilized by two of the phenyl groups. So due to this greater stability, the carbocation is formed in this position and the methyl group migrates here. Amino its name is 1,1-diphenyl 2-amino propanol. Okay, So this type of molecule also gives Pinacolone rearrangement reactions. Here, instead of using normal acid source like H2SO4, we will use HCl in presence of sodium nitrite. So it will generate HNO2, which will form a very good leaving group. Which will form means which will convert this amine group to a very good leaving group and to positive. Now from here it takes, the reaction goes in the similar way. This very good leaving group will eliminate to generate a carbocation in this position, and now the phenyl group from this position will migrate here and we will get a product which is this one. So these were some of the simple examples about Wagner rearrangement reactions and Pinacole Pinacolone rearrangement reactions. I hope you enjoyed this video.